All right, guys. So again, today we did this problem yesterday. Today I wanted to teach you how to name it. Naming dot waters is very simple. Do not overcomplicate it. Here's what we're going to start with. If you just saw that right there, MgSO4, Mackenzie, how would you name that? Very good. Magnesium sulfate. Now, we have to also incorporate the dot water, or the hydrate, if you will. And it's a very simple way of doing it. So you say magnesium sulfate, and then the number of waters turn into the prefix equivalent, if that makes sense. What is the prefix for 7? Hepta. Okay, so we're going to call this magnesium sulfate heptahydrate. Real simple. Magnesium sulfate heptahydrate. Some of you yesterday pulled up this worksheet right here. See if it's in Notability, please. A lot of you did it yesterday because I accidentally told you to pull up the wrong one. Awesome. Look at it real quick and scroll down to these two. See if you can name these two right here real quick. Take about a minute to do those two. Matter of fact, do those two and then turn the names into the formula. Again, name the original compound, and the number of waters turns into the equivalent prefix, and add hydrate. Whew. All right, still waiting, still waiting. All right, Bryce, iron what? Bryce, thank you. Bryce, iron what? Name it. Name it. Fuller, help him out. Iron 3 what? Chloride. Okay. What is it, Bryce or Fuller? Why hexa? Because it's 6, exactly. That's all you have to do. Okay, so the only thing new is adding how many ever their waters are plus the word hydrate. All right, Andrew, copper what? Try again. Very good. Copper 2 what? Sulfate, and then? Watch yourself. Very good. Penta. Okay. Penta. Now, again, I have never, ever, ever seen this next one on the exam where they actually give you the words and never give you the formula. But just in case, why not? So, barium chloride dihydrate. Hopefully you wrote BaCl2, the dot, and then 2 H2O. Is that what everybody got? Yep. Real simple. Don't overcomplicate it. Real simple. All right, so now let's go back to the other worksheet. We're pretty much done with that one. But I want to go back to this one, and I want to show you something, okay? And there's the reason why. If you will go down to the last two, please, there's a reason why I'm showing you this. Because yesterday when we did this, matter of fact, I will go back and show you this real quick. Remember how they gave you the total mass of the hydrate itself, and then they said after you boiled all of the water off, this is how much of the anhydrate was left. And how do we find how much water was boiled off? Simple subtraction. Well, what if they give you a problem like this one? Go all the way down and look at number 6, please. Number 6. When 8 grams of, what's that compound? Lead 2 acetate. And then it has XH2O. So you think your objective is probably going to have to fill in that X. So something hydrate. Are heated. Notice what it says. This is why I'm showing you this. 1.14 grams of water are driven off. So what's different about this one than the past ones? They give you the amount of water that was driven off. So if you go back, they give you the water. So what do you probably think you're going to be solving for? The anhydrate. Is that harder? It's the same thing. You're just going to swap these two things. So when you subtract, find the chemical formula and the name of this hydrate, it's the exact same process. You just subtract, but this time you're going to get the anhydrate, and then what do you do once you get the mass? Go grams to moles, and then you divide the mole of the water by the mole of the anhydrate. Everything else stays the same. Okay, so go ahead. You get the mass of the anhydrate and the water, convert both of them from grams to moles, and then divide the moles of the water by the moles of the anhydrate. And it's going to give you a number, and that number is how many waters there are. Okay, sir?
Do you always get the mass of the anhydrate and water?
Okay, you're going to have to, yes. But
you're given the hydrate?
You're always going to be given the hydrate, yes. Okay? You should always be given. Coleman, they may make it even easier and say, after you started with so many grams of the hydrate and the anhydrate had this much and this much water was driven off, then you don't have to do any of the subtraction. So that would probably be the easiest way they could do it, unless they do it this way. And let's look at the very last question. A hydrate is determined to be 45.43% water. Okay? Percentages. Don't let them freak you out. Stop. So we have that much water, and then we have 54.57% cobalt-2 chloride. Find the chemical formula and the name. Hint, assume that there's 100 gram total of a hydrate compound. So what did they just do? They've just given you the masses. How? Take the percentages and turn them what? Right into grams. So Coleman, this is the other easiest way to do it. They gave you the percentages, just drop the percent, change it to grams. Okay, I do want you to work this one out. So go ahead and work this one out.
Will they always say that there's 100 grams?
No, that's something you're just going to have to know. That's kind of like the empirical formula thing.
Is that given though if they give you percentage?
Yes, it's kind of an understood quality. Yes.
So when you change it from percent to gram, you move it 2 places with this one?
No, just drop the percent, turn it to grams. Yeah, just put a G. Just like with the empirical formula. Yep, just like with the empirical formula. I do want you guys to work that one out, though. So one more time. Why did we not have to do any subtractions? They gave you the mass of the anhydrate and the mass of the water, because all we had to do was take those percentages, drop them, and turn them right into grams. Then we converted grams to moles, and then we did the mole of the water over the mole of the anhydrate. Did anybody get a whole number there? 6. Very good. 6 was your whole number. So now we need to plug that in, and let's write it in the formula. So the final formula should be COCl2, right? It was 2, correct? Or 3? 2, thank you. Dot 6 H2O. So that will be your formula. Yes, sir. Okay. Yes. Mine was 0.4203. So, I mean, it's that 3, 1, let's see, 100,000, was that 10,000? 3 10,000ths isn't going to drastically affect your answer. Gotcha. Okay. Yep. All right. So, how would you name that? That would be cobalt-2 what? Excuse me, cobalt-2 chloride. Hexahydrate. Very good. That's how you name that. All right. So, we are done with the hydrate stuff. Are there any questions on that? Okay, if you have any questions, go back and work any of those other worksheets. I'll be glad to answer those. All right, here's what I want you to do. If you'll go back into Schoology, please. In Schoology, there's a worksheet that I would like for you to pull up. It is called Stoichiometry FR, and it has revamp in parentheses. It has revamp in parentheses. Has revamp in parentheses. And put that in Notability, please. Okay. All right, so let's begin. Answer the following questions about BeC2O4. We know Be is beryllium. What is C2O4? This is something you hadn't seen very often. It's oxalate. Very good. So this is beryllium oxalate. So we want to answer a question about beryllium oxalate and its hydrate. So what does that mean? What is a hydrate? We just talked about it. It's an ionic compound that what? Has waters attached to it. So specifically, what this particular hydrate is, the first question is calculate the mass percent. I'm going to stop right there. They want to know something about the mass percent. What do we know the basic definition of a percent is? Nope. The basic definition. Part over whole. All right. So we're looking for a part, and we're going to be looking for a whole. Do you agree? All right. So the mass percent. Specifically, we're going to be looking for mass parts and mass percentages, right? So there's an important thing. Of what? Of carbon. So do you agree that carbon is going to be our part of this compound? All right. Of carbon in the hydrated form of the solid that has the formula. All right. So here is our formula. So specifically, how many waters have been attached to this thing? 3. So this is beryllium oxalate, what? Trihydrate. Fantastic. All right. So here's the deal. We're looking specifically for carbon, correct? So of that whole entire hydrate, how much of that hydrate is specifically carbon? How many grams, because it says mass? How many total grams would that be? There's 2 carbons, so how many grams? Very good. 24.02. Fantastic. How did you find that, Jordan? Fantastic. 1 carbon is 12.01. We know there's 2 carbons in the compound. So it's 24.02. Now there is a trick to be able to figure out the rest of the mass of this thing. There's an easy way to deal with these waters instead of having to make it complicated. What's an easy trick do you think of solving how much water that would be? Perfect. 3 times 18.02. That takes care of the water part. All right, so 3 times 18.02. I'm just going to write this off to the side. That little part is 54.06. Okay? Again, that little part is simple. So what I was saying is you wouldn't have to do 3 times 2 is 6 hydrogens and then 3 oxygens. That just makes it complicated. You know that water is 18, so just multiply it by 18.02. And then add it to the rest of it. So we know that, let me just go ahead and do the rest of it. You guys could do this on your own. Times 4 equals plus 24 point. Okay, here's another question. Even though I'm looking for carbon and I already have 24.02, do I still have to include that 24.02 in the total mass? Yes, please don't leave that out. And beryllium is 9.01. So the total mass of this thing is 151.09. And then we're going to multiply it times 100. Okay, somebody with your calculator do that real quick. You should have come up with what percentage? I'm just going to say 15.9%. 15.9%. Is this question very difficult at all? The thing that made this question difficult was this big, huge compound, right? That's the only thing that made it complicated. If you see mass percent, anytime you ever see the word percent, you know it has to be a part over a whole. The part they were specifically asking about was carbon, and that big old compound's the whole thing. You should be able to have figured that out. If you got this correct, you've earned 2 points. 2 points. You earned 1 point for the correct percentage, and guess what else they gave you a point for? The mass of the compound, which you all should be able to get. Okay? Yes, sir.
That's what I was going to ask. Can you explain how you got the mass of the compound easily again? Because I know you said you could do all of them individually.
All right. Do you agree that you did that right there was 54.06? Okay. Yeah. 1 beryllium is 9.01. It's just finding the mass of any other compound. If I gave you water, how did you find the mass of water? It's just like that. You just have a lot more things to deal with. Yeah. And then 4 times 16 was, what, 64? Plus, yeah, just like any other compound. Okay. All right. So that's mass percentage. Let's move on to part B. When heated to 220 degrees Celsius, beryllium oxalate trihydrate dehydrates completely. As soon as you see the word dehydrates completely, what does that mean? All the water is gone. Every bit of it's gone. To represent the equation below, let me explain something. A lot of students mess this up. Does this dot right there, this in yellow, please look for a second. Does that dot in yellow and this plus sign in green mean the same thing? No. The yellow incorporated this entire thing as one complete entity. When you add the plus sign, what does that tell you about the things on the right? Are they separated or together? Completely separate. Students mess this up. They try to treat that dot like a plus sign, like those are two separated things. Guys, there's one reactant on this side. Just one. And it's that whole entire hydrated compound. That's it. Okay? So, that's the reaction. So, if 3.21 grams of that whole entire hydrate. So, do me a favor. Write 3.21 grams underneath that. 3.21 grams is heated to 212 degrees Celsius. Calculate. So let's look at part single I. The first question is, the mass of what specifically are they asking for? Okay. Where will you find that? No. Do you agree that it's one of your products? Just one of them. So this is what I want you to do. Underneath that one thing, write a question mark and then write G. Have you ever seen anything like this before? What are they asking you specifically to do? Gram to gram. Can you do that? What do you have to have specifically to go gram to gram though? Mole to, where do you get mole to mole? Coefficients. This is where again students mess it up. The coefficients come from in front of the compound. So what is your mole to mole ratio? 1 to 1. Do that for me, please. Go gram to gram. Guys, you don't have to write the whole hydrate. Let me kind of get you started on this. Was it what, 3.21 grams? All right, 3.21 grams. And just write HYD for right now. What does that stand for? Hydrate. Now, don't you already have the total mass of this hydrate? You've already solved for it? Yep. There's an easy way to find the mass of that beryllium oxalate without the water. How could you find it? Just subtract those 3 waters from it, right? That was 54.06 grams. Okay, go ahead.
So whenever we find, so whenever you have to use the gram here, would we use the ounces for like
that would be the total, it would be the 151. Yep.
That's what we use?
Yep. That's the grams of the whole hydrate. Yep. Was it what, 151 point what? Thank you. And it was a 1-to-1 mole ratio. Did you say what did you say the 151 minus the 54 was? 97.03. And that is again of the beryllium oxalate. Have you done stoichiometry just like this before? I mean, you're this, and if you notice, if you look back at the question, this was on the actual AP exam in the year 2000. This was on the exam that year. Okay? I can. Man, I know that was 14 years ago, but has much changed? I mean, in terms of stoichiometry, everything's the same. Nothing's changed in 14 years. Okay? So, when you do this, the answer you should get, and everybody should have gotten this answer because you know how to do this, was 2.06 grams of BeC2O4. And guys, that would have earned you 1 point for knowing how to do a gram to gram. Congratulations. You've been doing that since, what, Thanksgiving of last year? I mean, you should know how to do this. This should not be a challenge to you at all. And see, I think that's where students struggle the most in this class. Once I show you I kind of kick you down the right road, you're like, oh, I got this. It's reading through their wordy questions to determine what to do. I get it, and that's why this is training. I guarantee you by the exam time, you would be able to read that question and laugh at it because you're like, are they really asking me something this simple? You will know their procedures and their steps and the way they ask stuff because you're going to see it so many times. You're going to see how they work. All right? Now, I'm going to be honest with you. Do what? Double I is going to challenge you just a little bit. All right, let me scroll up, and I'm actually going to give you just a minute to see if anybody can figure this out. And I think you can. I had one person in first period or second period actually figure out what to do. I'm going to kind of push you just a little bit, Bryce, so you make sure you can kind of follow through this. Why does it hurt? Okay. How many times have you done gram to gram? Your brain shouldn't hurt. You should actually be excited that it's that easy. Okay? All right. Here's the deal. Here's what I want you to do. Double I. What they want to know, they're asking you to, please listen, they're asking you to calculate the volume of water that is released. We know that they've already given us 3.21 grams of this stuff, and then all of a sudden, they're asking us for a liter. Why did I write liter? Because isn't liters volume? Okay, that's all I've done. Liters is volume, same thing. They're asking us for a volume of water, and then they give us this weird stuff. They give us a temperature and a pressure. Everybody recognize mmHg? mmHg, millimeters of mercury. Pressure, not millimoles of mercury, no. Okay, this is millimeters of mercury. Let me push you. Let me push you. Hang on, let me push you. They're asking you for a volume, and they've given you a temperature and a pressure. So they're asking me for a V, and they've given me a T and a P. Huh. See if you can figure that part out. See if you can figure it out. Go ahead. Yeah, go ahead. Go ahead, Jacob. No, you will not leave it in millimeters of mercury. All right. Here's what to do. Some of you have kind of already figured out you need PV equals nRT. Do you agree? You should need that. Let me pause you for just a second. However, here's the deal. Do you agree that you need water? Yes? Yeah. So watch for just a second, okay? PV equals nRT. Everybody with me? Specifically, what are you wanting to get out of PivNert in terms of the values and the variables? You're wanting to get volume. Do you agree that you're wanting the volume of water? Everybody okay with that? That's the question. Volume of water. Rearrange PV equals nRT for V. What would it be? Now, here's the deal. What does N represent? Number of moles. Now, here's the problem. They've only given you grams of this thing, right? What are you going to have to do? Convert it to moles of water. So I need the N of H2O. I'm going to need R, which I'll give you in just a second. I need T, and I'll also need P. All right, what's wrong? What's the question? Go ahead and ask. All right, that's a good question. I need the volume of water, right? I can't get grams of this, They gave me grams of this thing, right? I can't find the moles of this and compare it to volume of water. You have to compare the same compounds. You with me? Okay. If you're going to find the volume of one, you have to at least have the moles of the exact same compound. Okay. So the first thing I want you guys to do is convert 3.21 grams of the hydrate to moles of water. It's a two-step, and you already have one of them done. So if you'll look right here for a second, I'll erase this, and you can copy this. Do you agree that that's all you would need right there? Yes, you do. Guys, you have done this 100 times. I went from grams of the hydrate to moles of water. Where does the mole to mole step come from? Coefficients. What was the mole to mole ratio? 1, 2, 3. Remember, because in the hydrate, how many waters were there? There was 3 waters. That is going to give me this many moles. It's going to give me that many moles of water. All right, it's going to give me that many moles of water. All right, so let's go back to that thing we were working a second ago. So what is my N numerical value? Okay, so 0.0627 moles. Sorry, 37. Our next variable is R. Do not say it out loud. I want you to think for just a second. I've told you before there's a gas R and an energy R. Which R are we dealing with? Why gas? Because we're dealing with volume and we're dealing with pressure, right? So the numerical value is 0.0821. Do you have to memorize that value? Remember, it's on that formula sheet, right? You're going to get on that on the day of the exam. Absolutely. 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 Every test you ever take, you'll get the periodic table and you'll get the formula sheet. Guys, it is a cheat sheet. Use it like one. All right, we're going to get there. What is the unit on this R? Latum over molk. All right, so what that just did is that just defined all of our units. So if you're dealing with things, what must the unit of volume be in? Liters. What must your pressure be in? Atmospheres. What must your temperature be in? Kelvin. All right, so there's an issue. The temperature that they gave us was what? 220 what? Celsius. Do you remember how to get it to Kelvin? Add 273. So that's going to bump it up to 493, right? That's going to bump it up to 493. And the last thing, guys, I'm going to be honest, this next part is rare. I very rarely see it where they give you millimeters of mercury They very rarely ask you to convert that. In this case, we do have to convert it. Does anybody actually remember the conversion factor? And I'm just going to write it up here. In 1 ATM, there were so many millimeters of mercury. 760. 760. If you don't remember this, let me show you this real quick. Please excuse the drawing. I'm not a profound artist. Okay? What this is a petri dish with mercury in it. It is a petri dish with mercury in it. Okay, stop. I get it. Let's try this again. Y'all are high schoolers. Y'all are so immature. All right, so this is a petri dish with a column coming out of it. Can't show you guys anything because you're a bunch of jerks. Okay? All right. Now, this is mercury in the petri dish. When there is 1 ATM of pressure pushing down, again, this red is 1 atmosphere. What that's going to do is it's going to push up the mercury exactly 760 millimeters. That's where that comes from. So 1 ATM pushing down pushes mercury up 760 millimeters. That's where it comes from. Okay? So, that's not what I want. I want this right. That's not what I want either. Okay, there we go. So, how can we convert that? We can take 735 millimeters of mercury, and in 760 millimeters of mercury, how many ATMs? 1 ATM. So, if you want to convert it, all you got to do is divide. So, thank you, sir. 0.967 ATMs. Now, again, I told you, that is a rare thing for you to have to do on the actual exam because it is a waste of your time, and they don't want to know, can you convert stuff? They want to know, can you do the math part?
So you want to do that?
If it shows up, I'll be glad to tell you. Okay, I'll give you the conversion factor. I'm not going to convert it for you, but I'll give you the factor. How's that sound? Okay. Like if it ever shows up as millimeters of mercury, I will give you this thing, and I'll say make sure you convert it. Okay. Yes, sir.
So do we need to know the 273?
Yeah, that one yes, the temperature definitely will show up. Because that one is so common because we don't ever measure rooms in Kelvin. We do measure them in Celsius and that's a lab-based thing. Okay. All right, so when you do this math, I'll go ahead and tell you that the answer that you come out with is going to be equal to 2.67 liters of water vapor. Now, I said vapor. Why did I not say liquid water? It was heated, and then go back and look right here. Let me clear all of this. What state of matter is that water in? It's a gas. Okay? No. I said it verbally, liters. Or vapor. I do want to point this out. I want to show you unit cancellation because I do think it's important. Do your moles cancel in your work? Yes. All right, notice, look, your moles cancel. What else cancels? All right, your kelvins cancel and your atmospheres, leaving you with liters. I should have done that before I ever did the answer, but I want to show that because it is important. You may screw up every single one of these numbers, and you may get the answer wrong, but I'm still proud for the fact that you worked it out. But if you work all this out and you give the wrong dadgum unit, that's when you're in trouble. Okay? Please don't give the wrong unit. If it's asking for volume, please don't put pressure. Be smarter than that. You're in here for a reason. Okay? All right. Do what? That's true. All right. Here's the last thing that I want to talk about, and I want to add this. Let's pretend that number 2 did not read this way. It read a little bit differently. So I'm just going to say this is like part B double I, or excuse me, double I part B. It was measured at STP. This is much easier than what we just did. So I need you to know that this is going to be easier than what you just saw. The first question I have, and some of you may not know this, what does STP stand for? All right. That's what I got to have. Standard, temp, and pressure. That's what it stands for. Standard, temperature, and pressure. I would. But here's the key issue. What are the standards of temperature and pressure? Anybody remember? That's part of it. Very good. 1 atm and 0 degrees Celsius, or what is that in Kelvin? 273 Kelvin. And this is the most important fact, this next piece of information. The most important fact. At STP, 1 mole is equal to 22.4 liters. And I know what some of you are thinking, where in the world did that number come from? And I'm fixing to prove it to you. Fixing to prove to you where that number comes from. Just a minute ago, I showed you PIV-NERT, or the ideal gas law. PV equals nRT. Here's what I want you to do. We've already said this once. V is equal to nRT over P, correct? Go ahead, Matt.
What's the purple stuff from the
This right here, this purple are the conditions. That's the standard temperature and the standard pressure. All right, here's what I want you guys to do. According to the purple and the orange, what would the N value be in this formula? What would the N value be? 1 mole. R is always going to be 0.0821, right? What would T be? 273 K. And what would your pressure be? 1. So you'd agree the only two values are 0.0821 and 273. Do me a favor, in your calculator, multiply those two numbers together. 0.0821 and 273. Don't say it out loud when you do it. Multiply 0.0821 times 273. And what number did you get? 22.4. That number is legit for a reason. It's not something we make up. That's where it comes from. So, this is very important to you. Extremely important. So, can I show you how much easier that problem would have been had it been at STP? The question was what? Calculate the volume at STP. So, here's what you could have done. All right. Let me erase all of this. Do you agree that you have the moles of water now? Watch this. 0.0637 moles. And in 1 mole, there are 22.4 liters. And you're done.
Wow, that's pretty cool.
That's all you'd have had to have done. But when is the only time you can use this relationship? At STP. That's it. This is the only time you can use that. That's it. Go ahead, Matt.
So, if they give it to us in STP, that's all we're going to do.
You have to at least find the moles first.
And then just do that?
And just do that. That's it.
Like every time
You don't even have to do PIV-NERT because 22.4 comes from a derivation of PIV-NERT. That's why I showed you, when I asked you to plug it into this, that's where that value came from. Basically, you're eliminating that whole step. There's no reason to do it. Okay? So, STP makes things much easier. That's why when they do most lab experiments, they try to conduct them at STP for that specific reason. It makes everything a lot simpler. Okay? All right. How much time do we have?
A minute.
All right. We'll stop here for today.
Thank you.
Don't forget, tomorrow after school starting at 3:30, I will be doing a review session. I will record it, but try to be here. It is a come and go as you need to. If you need to come in a little late, if you need to leave a little early, that's fine.